Okay, good afternoon. Wow, it's too loud. I'm very happy to be here in this interesting and large conference after 2 years of the corona. And my topic today, what I'm going to discuss in the next 20 minutes or so, is actually the function, the role, the mission, the contribution of AI, artificial intelligence technology, / machine learning, to the green energy era. But in order that all of us will be on the same page, what is AI actually, what it is done? So the definition is that it's actually a technology that exploits the ability of computers or robots that are operated by computer to do the tasks that are done typically by human beings. And how is it done? It is done by the computers or the robot actually mimic the behavior of us, analyzing data, and then come to conclusion, recommendation, and decision making. And actually the technology exploits the vast calculation power of the computer, which can do in a split of a second or a split of a minute, enormous amount of interaction, whereby our brain will do it in a day, in a week, or even more than this. The elements of the technology, it exactly simulates the element of our brain. We retrieve the data, we analyze it, we learn it, we do a strategic thinking, and then we take the conclusion. Today, the artificial intelligence actually is embedded in most of the business areas. I just listed some of them: transportation, self-driving car, health, diagnostics, algo trading in finance, travel, booking and flights, social media, smart assistant. Maybe you are familiar with Alexa. If now I call Alexa and I ask her, Alexa, what is the most popular song in Turkey? Well, she stayed in the United States, so she was not here, but in principle, this is actually an assistant of Microsoft who helps us in any question that we have in our premises. And e-commerce and so on and so forth. So the AI impacts our lives on a daily basis. But coming to energy, energy actually was the last one in line to implement the AI. And what is the reason for that? If we are looking at the traditional vertical network, actually, on one hand, there was not much data available. On the other hand, there was no demand, no request, no need to analyze data along the electricity chain. And if we look at the typical vertical system of the past, actually the energy is flowing in one direction. We start with the power station, going to the substation, going to the trafo station, and by low tension lines to the end user. So everything is done one direction, one flow, no interruption, no need for much data along all the segments of the chain, except for troubleshooting and preventing maintenance. But today, when we are shifting from vertical energy to distributed system, and I don't think that I need to explain to this audience the meaning or what is included in this idea of DER, of distributed energy, but in any case, we see the market share of the PV and the wind. We see 80% plus in EV, in electrical vehicle. We see 200% and plus growth in batteries. And what is more important, in the last year, the prices of the energy of the batteries went down, so the kilowatt-hour price might reach, depends if you are optimistic or pessimistic, might reach about $150 per kilowatt-hour, which will make it affordable and economical even for a single household. And last but not least, the smart meters. Today we have all over the world more than 100 million smart meters, replacing the electromechanical old one. And this is the most important element in our discussion, because the smart meter, these are the focal point whereby we can retrieve information from each and every single household, from each and every single end user. In shifting from vertical to distributed energy, the main issue is the data. As I mentioned, data is the king. And I give you two examples. Let's take the renewable. The renewable generation are not predictable. They are unpredictable because you cannot control, for example, this conference hall, if he has a rooftop PV, you can't control when he's going to consume the energy or when he's going to inject the energy into the grid. It very much reminds me the area of introduction of the internet, whereby there is no system manager to the internet. You cannot control the upload and download of people. They are doing it independently and in random, and actually it's a system without any possibility to be managed. Same thing is starting to happen also in the energy network, and this is a very, very difficult problem and major problem for all the system managers in all the administration around the world. If we take another example, what I call the energy politics, today all of us and the governments and politicians are triggered towards a reduction of emission. This, of course, involves shutting down the traditional power station like diesel for coals, of course, coal, maybe even natural gas, even though this, to my estimation, will take at least another 20 or 30 years. But in any case, in order to achieve all the targets of the reduction of the emission, you need to shift to the distributed energy, which by doing so, again, you have a problem that you need a lot of data in order to manage it. So if we'll drill down and we see and ask ourselves what an automated data science platform is doing. So first of all, it's forecasting. This I will elaborate a little bit later. Then we have the issue of profiling and clustering. Look, if I am an operator and I have, let's say, 1 million households, and now I have access to the consumption and to demand curve on each and every household. So I cannot handle 1 million customers, each one in a different way. So the idea is to cluster, to see what are the similar behavior pattern of groups of customers. For example, a family with children who stays all day at home, a couple without children who is all the time outside the home and come only in the evening, and so on and so forth. And then, instead of handling each and every one of the million households, actually we are dealing with 10 groups or 20 groups, which makes sense. Then we need to do portfolio optimization. Again, let's take this conference room as a conference hall as an example, and let's just imagine that they have rooftop and they have a battery in the basement and they have 50 EV chargers in the parking lot and maybe even a mini power station operated by natural gas if it come up to here. So someone has to say automatically to the conference hall here what to do every 15 minutes or even every 1 minute, to buy to the grid, to sell to the grid, to consume from the PV, to send to the battery or consume from the battery. So all this is based on two things. First of all, the data that we retrieve about the behavior of the whole on one hand, and second, it depends, of course, on the different means of generation that we are utilized in this premise. Also, in energy optimization, if we take the previous example and we add to this the prices of the grid, and let's not take, I don't know exactly what is the situation in Turkey, but let's take, for example, Texas, US. In Texas, you have about 300 different packages, like in the cellular, 300 different packages of pricing. And believe me, no one can really analyze what are the pros and cons of each and every program. So here, once you take the elements, your demand curve, and you compare it to the various pricing groups that are available, you need software that will do the optimization and will tell you exactly when to buy from the grid and when to sell from the grid. So I have listed here several applications of the artificial intelligence related to the energy sector, but it boils down to 4 main issues. One is forecasting, other one is optimization, the third one is demand-side management, and last but not least is preventive maintenance. And along these 4 main topics, we have a lot of subsystems that drill down and give us a more accurate information. Let's spend a few minutes about forecasting. And let's see what was forecasting yesterday with a vertical system and what is forecasting today when we shift to the distributed energy system. It's like moving, my background is telecommunications, so it's like moving from Web 1.0 to Web 2.0. So first of all, yesterday we had large producers. Power station of coal of 400 megawatts, 800 megawatts, 2,000 megawatts or whatever. Today, we have the renewable. The rooftop is even not in terms of megawatt, it's in terms of kilowatt. But even in the PV fields, we have several 20, 30, 50, 100 megawatts. In any case, it does not amount to the big, large coal power station. Yesterday, the electricity flows downstream. Today, as I mentioned, the electricity flows also upstream because each one that has a certain means of renewable energy can, on one hand, consume and, on the other hand, produce and send to the grids. So we have here 2 directions. And of course, we have the smart meter data available, which was not available in history. And this actually, I think, is the game changer that really gives us the information to have a big chunk of data out of which we can make our conclusions and our recommendation. And last but not least, all this boils down to the fact that previously the forecast was done from top to down. What do I mean? You took, for example, in Istanbul, the weather, the humidity, the irradiation, if it's a working day or a weekend, and so on and so forth, and you implement it for the whole city. Today, this still exists. This is the second layer. But the first layer, you do a specific forecast for each and every household, which means that if, for example, in this area, we have 1,000 households, in order to do the forecast of the neighborhood, we are not going to do something in general, depending only on external factors, but we are going to analyze each one of the 1,000 end-user smart meters and aggregate it so we have the whole forecast for the whole neighborhood. Here I just wanted to illustrate what I presented yesterday. On the upper diagram, you see a flow on one way, no interruption. And then below it, we have the interruption of all the type of renewable energy, of batteries, of EV chargers that suddenly are penetrating to the network without anyone telling them when to penetrate, when to do something or not, so you cannot actually control all these peripheral elements. But to do a forecast bottom-up, even if you use all this machine learning and artificial intelligence, it's not so easy. And I'll try to focus on 2, 3 examples. First of all is the data availability. Today, we have 100 million smart meters, but we have much more all the old meters, the electromechanical meters. So actually, we don't have enough data behind the meter, and we need to somehow to integrate between the smart meters and the dump meters and make the calculation based partially on data and partially on probability and prediction. Then is the issue of data handling. Again, imagine this, if I'm a utility of 1 million household, and the smart meter actually gives me or provide me each 15 minutes with a ping about the consumption in each and every household, it's exponential data. So you need somehow to handle it, to understand what to do with it, how to minimize it in order, or to aggregate it in order to make the right conclusion. Not easy. On the other hand, these 1 million smart meters, each one of them actually give us a very, very tiny information. An information about a consumption of a household, which is few, 20 kilowatt hours, 30 kilowatt hours. So on one hand, we have a lot of data. On the other hand, the data, it consists of a lot of tiny inputs coming from the end user. All this should be manipulated and crunched by the artificial intelligence, and actually this is the smart part of the job. Speaking about forecast, so basically there are two levels of forecast. One level is for the businesses, what is the most important for the providers, and for the C&I, for the commercial and industrial segment, is the load forecasting, the consumption, because this is the key issue that each one has to understand. What is the forecast a day ahead, week ahead, months ahead, in order to know how to calculate and how to manage buying electricity and selling electricity. And in order to explain it, I would like to give you an example, a case study. And OPC is one of the, I'm coming from Israel, by the way, I didn't introduce myself. So OPC is one of the leading IPP, independent power producer in Israel. They stand today, I believe, for about 7 or 8% of the total consumed capacity. And as in all over the world, they have to provide each day by 4 o'clock a forecast day ahead. Now, a year ago, the regulator, the PUA, the Public Utility Authority, actually changed the regulation and imposed fine if your forecast has a deviation of plus 3% or minus 3%. And suddenly, the issue of the forecast became a major issue for the profit and loss, for the profit line. So what they have done, this company has about 500 C&I, commercial and industrial customers. In Israel, by the way, the IPPs are allowed to sell only to commercial and institutional organizations, not yet to the private sector. It is coming, but not yet. So they have 500 meters, and they implemented the idea of doing forecasts from bottom up. And by doing so, they achieve a 30% improvement in the accuracy of the forecast, which results in about, if I'm not mistaken, $400,000 per year. So here we can see the importance of understanding exactly how to calculate, how to forecast, how to implement the machine learning technology in order to have a smooth operation and to improve our profit. So what I'm trying as a final note, so artificial intelligence, and I'm not diving into the specific of all the algorithms. Believe me, it's a lot of a headache. But basically, it's a key issue in accelerating the energy transition from the vertical to the distributed energy. They expand access to energy services. What is maybe very important, and I'll devote a minute to this, it encourages innovation. What do I mean? 10 years ago, I was the president of the Israel Electric Company, and at that time, I initiated an incubator for startups dealing with energy. So 10 years ago, I could barely find 5, 6 startups because all the high-tech community in Israel was focused on software, telecommunication, security, cybersecurity, health application, and so on and so forth. Energy was not part of the game. Today, I think that we have, last time that we checked it, we have about 100 startups doing several R&D developments relating to energy. And what is the reason for that? Exactly what we are discussing today. Energy actually is going through the same changes that telecommunication had gone like 30, 40 years ago. End of monopolies on one hand, and a new technology, a breakthrough technology, a new paradigm that's changed the world. In the telecommunication, it was the fiber optic. The fiber optic brings us the internet, the social media, and all the rest is known. In the energy, first of all, end of monopolies almost all over the world, and then the shift between vertical to distributed energy actually brings up the necessity of having a lot of data and understanding how to analyze it. But what I can say as a final note is that technology by itself, at least that's what I believe, technology by itself cannot achieve the goals. Beside the technology, you need a commitment of the politicians, of the regulators, of the business society, of the business environment, of the managers of the big companies, of the public itself that would like to achieve the goals that we can achieve by implementing the AI technology. And this is, first of all, to have a better and economical network, and second, really to reduce emissions, and this is in context of the general topic of this conference. Thank you very much for your time. If there are any questions, feel free to do it. Okay. Yes, please.
I would like to ask, what do you mean by artificial intelligence? Is it really a self-learning algorithm or a very complex, the conventional, let me say, algorithm?
No.
Maybe you can,
sure.
talk about artificial intelligence in this sense a little bit.
Let me dive in for a second just to explain. If I take this application of forecasting from bottom up, behind this you have about 40 algorithms that are analyzing each and every segment or parameter of the data that is coming, and then first of all, it's analyze each and every segment, and then it integrate together to have a one solution. So basically, the type of expertise that you need in order to be part of it really comes from, I would say, computer science, mathematics, maybe even physics, because you need to know how to play with the data and how to crunch it so you get the right answers.